Well, we saw the chord-chord product theorem. We saw the secant-secant product theorem. You're probably wondering what's left. Well, of course, it's the secant-tangent product theorem. You probably saw that coming, maybe. All right, the secant-tangent product theorem is really just a sort of a generalization, if you will, or a sort of a different case of the secant-secant. Secant-secant said I had two secants. I'm taking now one of the secants and pulling it over until it just grazes and becomes a tangent. And here's the truth in that situation. Notice that here I've got this piece and this piece, but only one piece here because it only hits this circle at one point, unlike the secant that hit at 2. So what's the result? The result is what you might guess, which is that AC, this entire length, multiplied by BC, is going to equal this length squared. So this length multiplied by itself, which is what you might have guessed if you thought about it a little bit. Let's take a look at an example and see if we can figure out what x has to be here. So here I know that this right here is 9, this length is 7, and I'm trying to figure out what the length of this line segment is, which is called x. Well, how do we proceed? We know that this entire thing multiplied by this is going to equal x squared. And so I see that x squared has to equal this entire length, which is going to be 9 plus 7, which is 16, multiplied by this length, which is 9. Now I'm going to do a little mental math here and have some fun with this. You can actually multiply that out and see that it's 144, but let's pretend you didn't see that. What I'm going to do now is just take the square root of both sides. Now, of course, whenever you have a square, there are two answers, right? Two answers, and we have to figure out which one we want. Well, in this case, x is representing a length, and so therefore we know that x has to be positive. So I can just take the positive square root, and I'm going to use a property of square root that tells me that the square root of 6 is 4, multiplied by the square root of 9 is 3, and so I see the answer is 12, which, by the way, is what we would have gotten if we would have known or multiplied this out and see 144. The square root of 144 is 12. Anyway, the answer is x equals 12, and we were able to actually find that length, AD, by using the secant-tangent product theorem. Another beautiful theorem, which really, in some sense, corresponds quite well with the secant-secant product theorem. Lots of product theorems that link products of lengths of various line segments when you're thinking about chords, secants, and now even tangents.